Assalamualaikum warahmatullahi wabarakatuh. Let's meet up at the topic of or chapter 11, angular momentum. Something to ponder which you have seen earlier in the previous topic. A linear momentum is a product of mass time velocity. So therefore, quite similar to what you have seen earlier, we will as well find the concept of when an object rotating and having v. Therefore, we should find it's also possessing what we call as angular momentum. We have 4 subtopics to be covered within the chapter 11, and these are the example and including the tutorial questions related to this topic. So before we really dwell towards the angular momentum itself, we have to go back one step backward and study again what we call as vector product for the torque, or what should we call cross product. Now, it's called cross product because it must be perpendicular with one another. So you have seen this in the idea of torque earlier. For instance, the product of torque, okay, is R and F. They must be perpendicular, and you find that the direction is indicated as in the figure here. Okay, but overall the idea should be saying that R times F is equivalent to C, where if it's the other way around, or should we say F times R, the direction would be in the opposite direction. It's also interesting to recall that since torque required R and F to be perpendicular with one another, and that's the reason why you find that it's a cross product, where else work is what we call as dot product, where dot product required us to ensure that R and F are parallel with one another. Therefore, in the view when the angle are not perpendicular with one another, for instance less than 90, observe that the torque itself is a product of R, F, sine theta. Okay? Now, there will be an additional video accompanying this so that you can understand how we can do the calculation later on when it involves IJK process. But nevertheless, something to take note, that when you cross product A and B, it's actually negative of B times A. So we will prove this later. And when you have a vector which is parallel to one another, then it becomes 0. Remember the work process that you need to, the force product and also the displacement product should be parallel or anti-parallel. So if we are making them cross with one another, you end with 0 value. And therefore, if it's perpendicular, then straight away it's the product of torque itself that you have seen earlier, which in this case is AB. And at the same time, you can as well factorize it, okay? Or we call it obeying the distributive law. And finally, this is how the derivation with respect to some variables will look like. Alright, another things to note as well, remember that when it's parallel or anti-parallel, and recall that I represent the direction of x component, so here is as if like x times x component, so we have two forces R and F, but they are parallel to one another. So however, this one is parallel in the y direction, and here parallel in the z direction. That's why when you cross together this value, you have 0 value. And I and j, we have seen this earlier, when I, x and y, okay, is actually negative product. The answer is actually negative to the answer if we have it the other way around, okay, and you arrive with key product z direction. Remember talk earlier, the thumb direction, that's how you decide that it's k, okay, and it goes the rest. Alright. Alright, in the example 11.1, we are going to verify that product of A cross B is equivalent to negative B cross A. Now, aside of the technique shown here, where we should arrive with 7K, okay, I and J will arrive with K. When I, J, jawapan dia K. Macam tu. Okay. So, you should find that we can as well opt to solve using this technique. So, this is the A just now. And then B at the bottom. Negative 1, 2. So they should cross with one another. So 2 times 2 is 4 minus, the generic rule is minus 3 times negative 1. So negative 3. So the answer becomes 7K. 7K here. Now when we have it the other way around, B, we start with B, then cross with A. So the arrangement becomes, so B value is negative 1, and then 2, and then 2, and then 3. Let's cross them. So negative 1 times 3 becomes negative 3, then minus 2 times 2, which is 4. Okay. So altogether is negative 7K. So yeah, correct. Now, in example 11.2, rather than have A and B as a vector, we're going to use what we have learned earlier, which is in the concept of torque. So, given here is we pause in the X and Y component, where 2I plus 3I 3J hat, and the R value, or what we call as moment value, is 4 and 5 in the X and Y direction. So find torque. So to get torque, remember that it should be R cross product with F, not F cross product with R, or else we end with different answer. And for that to happen, okay, let's try. So aside of technique, this technique, so you should see that mathematically it's also correct to have this. Okay, except that 4 times 2, 4 times 3 is 12. Okay, and then 5 times 2 is 10. So minus 10. So the answer is 2 in the direction of Z, which is K, and the unit is Newton meters. Right, let's turn to subtopic 11.2, where non-isolated system, where we will go to the core idea of the topic itself, which is angular momentum. Now, in terms of the calculation, you will find that it involves a product of R cross product with the momentum. So this is how to measure or to calculate the angular momentum. However, okay, hold on. Okay, this is the equation that we are going to use, right? So I'm going to show a little bit on how we arrive to this conclusion. So how is that? By recalling the process whereby if let's say, okay, in this translational motion, object is moving in the x or y direction, we find that the momentum, which is F times delta T, can be written as delta P over delta T. Okay, so very similar to what we call it as impulse momentum theorem. So this is our core discussion. Now, in the case of a torque, okay, to make sure that it has some relationship to this, so let's look in this version. R times the F, which is the product of torque itself, is as well therefore equivalent to R times delta P over delta T. So by this version. by writing A is equivalent to R and B vector is equivalent to P in such, okay. So when we open up, okay, kembangkan, kita dah akan dapat this version, okay. Data R over data T times P plus R data P over data T. It's interesting to note that this is a cross product. So since it's a cross product, because dr over dt ni is actually V, and while P is actually mV, they are actually occurring parallel to one another. And because it's parallel, that's the reason the cross product of this expression becomes 0. So left only R times delta P over delta T sahaja. Okay. So in short, okay, when we equip, okay, with the left side just now, that delta R thought is delta R times cross product with P over delta T, we find that it has this similar expression to delta P over delta T, which is this one, okay, very similar to one another. So that's the reason why somehow we can suggest that combination of R cross product with momentum will give us what we call as angular momentum. So that's how we arrived at angular momentum with symbol L as R cross product with P. Cross product with P. What is P? P is mass times V, which is a linear product. Okay. So we have the two must be crossing with one another. And another thing to note, remember earlier F times T is delta mv. Alright, so this is momentum change. Okay, so this expression is similar to this one by considering ataupun analogy dia that torque is quite similar to the force, whereas force is the one enables system to accelerate linearly. Torque is the one responsible accelerating in angular ataupun dalam bentuk membulat, rotational. Right. Now let's turn to example 11.3. Now, in this example, we have two ideas that we would like to understand more. Number one, how is it that we can produce R cross product with P? Okay, R cross P. So here you will find that P is a product of mass times V, the momentum itself, whereby it's a linear momentum. Therefore, this is a tangential direction. So tangent product of V. And the thing is, the axis of rotation is exactly at the center. So you find that the R, okay, or moment is actually perpendicular in terms of the direction with the tangential V. And therefore, you find that similar to the calculation of torque in where you include the angle, so you find that the angle here between both is actually 90 degree. And at the end of the day, the product of momentum, angular momentum to be precise, is just a product of mass times V times R. So the second thing that we would like to evaluate is the direction, because angular momentum is a vector product. So by using right hand rule, you find that your thumb is out of the page. Okay, that's one way of looking at it. So since it's out of the page, we find that that would be a positive value of angular momentum. Another way to look at the direction is the similar method you use in determining the direction of the torque, whereby where would it rotate? So in this case, you find that the rotation is counterclockwise. So again, okay, similar to the concept of right hand rule, where your thumb is out of the page and you end with a positive product. So likewise, if L is pointing downwards into the page, okay, opposite direction of everything, so you will find that is a negative product of L. And this as well, whereby it moves clockwise.